All right, thank you. And I'll start off by thanking you all for putting up with a presentation in English today. So my Spanish is way too rudimentary to try to tackle this topic in Spanish. Okay, so I was asked to talk about adequacy and resilience. And so I think I will start by sort of setting the stage about what these topics mean and why, if they are even different. There are many definitions out there. Perhaps Columbia has your own definition that you work with, but sort of looking at some standard ways that we talk about adequacy in the research community, it's basically supplying power, right? Being able to meet the demand all of the time. If instead you look at definitions of resilience, we say, hey, wait a second, maybe there are times where we don't meet the demand, where we don't supply all the power. And perhaps that's okay, recognizing that there are some really bad days and some really extreme situations that warrant not serving all of that demand. Okay, so the definitions are different, right? They use very different words for adequacy and resilience. But when you think about the challenges, right, what it means to address adequacy and address resilience, we have load growth, we have electrification, we have changing generation, right? We have increasing dependence on weather for our generation. And then there are common cause impacts that can affect vast areas of the system at the same time. That's the same for resilience, right? We've got these same challenges for a resilient system, thinking about future load growth, future electrification, future changes to our generation resources. But there are some other words that are often thrown about in the resilience space, right? Resilience is often thought about as coming hand in hand with, increasing frequency and severity of these high stress events. I'm purposely not using the word extreme because extremes are changing in a changing climate. And what is extreme today from a statistical standpoint might not actually be extreme in 20 or 30 or 50 years. But so you have these sort of increasing extremes that are really driving these questions of resilience and driving the increasing research in resilience. And I'd argue that you also see this increasing dependence on electricity. So mostly we're arguing that resilience is important because electricity matters more to people. So maybe that first one is the same for adequacy, right? Adequacy is also concerned with these increasing high stress events, changing frequencies and severities of these weather conditions. But perhaps this one is still unique to resilience, right? So resource adequacy cares about, okay, an outage happened. We did not serve the load. That means we are not adequate. Whereas resilience is talking about, because of this dependence on electricity, we care that we didn't serve the load, but we also care about why. What happened as a result of that lost load? What happened to the customers, what happened to critical services, and perhaps this is a different way of thinking about resilience if you want to separate it from adequacy. Okay, so if they are different, then how do we go about assessing them, right? With adequacy, in many cases, we have standard agreed upon metrics that we use. We can look at some numbers and say, yes, we meet our adequacy targets. We check that box and we are good. These metrics are concerned with losses of load in terms of frequency, duration, magnitude, but in general, you add up all of your outages and they all come into a single metric, and you can sort of think about all outages as being treated equally. Resilience does not have standard metrics, right? We don't have accepted ways to think about resilience. We can use resource adequacy metrics, we can use these lost load metrics to determine whether or not we are meeting our targets for resilience. But if you think about the fact that resilience is also concerned with these broader aspects of preparation, response, we don't have metrics around whether we were prepared enough before something bad happened, whether we responded appropriately while the event was unfolding, whether we had resources in place to restore quickly and recover after an event. And there also might be aspects of the outages that are not equal, right? Outages that are widespread and long duration perhaps matter more from a societal impact perspective, even if they add up to the same total outages from your adequate system. We also might care more about disruptions to critical loads or disruptions to vulnerable communities, whereas in the adequacy space, again, those are all treated equally. So it's hard to define these many aspects of resilience with any single metric. There are many folks working on perhaps putting together suites of metrics to try to capture that space, but it is really complicated, and the answer might honestly vary based on the type of hazards that you're concerned with and the type of system that you're operating. Okay, so that is sort of how we think about adequacy and resilience, and so maybe it's worth talking about whether today, are we adequate and are we resilient? And I only pulled a few examples, but perhaps looking at these examples, you could say that no, we've had some really drastic events over the last few years showing that our system has not been able to meet the challenges that it's faced with. Perhaps the news from Texas has reached you all in Colombia, but we had a devastating cold snap event in Texas where the power system failed partially as a result of the gas system failing. So perhaps there are also aspects of resilience that depend on external factors and interdependencies, which again warrant different metrics to be used. And we've also seen challenges during increasing heat waves as a result of climate change, which is really stressing the system both from a supply and a demand perspective. Okay, so if we're not adequate or resilient today, then let's think about the future. And again, this is an example for the US, but we have projections saying that even in the next few years, even knowing what we've dealt with in the last few years, we are not expected to be adequate or resilient going forward, right? We have this high risk of not being able to serve demand over just the next, in this case, few years. Also looking forward, there is some good news, right? We have some good news of folks being proactive, recognizing these challenges for adequacy and resilience, and recognizing the changing climate and what that brings, and being able to address specific periods of high stress. So here's a really great article about how California had seen adequacy challenges during past heat waves, but with increasing additions of solar and batteries to ride through what really is a few critical sunset hours in the state, they've been able to manage more recently quite well, right? So there are things that we can do to address adequacy and resilience, but they take different types of planning. So if we're thinking about how we typically plan the power system, right, we have some traditional planning uncertainties that we all are well aware of about load growth, variability in renewable generation, variability in fuel prices, perhaps any changes to the policy or regulatory environment, and we know how to put those into our models. There are other uncertainties that are becoming more and more important to consider. Electrification is changing both the amount of load and the way those loads behave on the system, more in some places, less in others, and so again, there's no one-size-fits-all solution. Climate change is a massive driver of risk for our power systems. Climate change also impacts severe weather events, so these sort of go hand in hand, and again, there's a lot of uncertainty about these things. It depends on what we do. And the extreme events are not always perfectly understood when it comes to how they'll respond to global average climate change. With climate change and with extreme events, they impact our assets, right? So we know they're changing the environment, but what it means for the assets that we rely on, again, requires a new type of thinking about how those vulnerabilities may be manifested and how we can best represent those in our systems to make sure that we are not being overly optimistic in how we account for the performance of our generators, our lines, our transformers, et cetera. Each of these, if you start to sort of think about how they play out, impacts both supply and demand. So if we're trying to look at a future system where we can balance supply with demand, we have to think about the ways that electrification, climate change, severe weather, and asset vulnerabilities impact both of those pieces of the equation, right? And this makes for a very complicated planning challenge if you're trying to capture the interdependent ways that electrification can both help you and hurt you during any type of climate situation. So a quick plug for some of the work we're doing at EPRI. We've recognized all of these planning challenges. We've heard from many utility companies about these planning challenges and about the fact that there is no agreed upon or standardized way to go about planning for climate risks more productively. And we're coming to the tail end of a 3-year initiative called Climate Ready, which is tackling this from the standpoint of better understanding the climate data, the vulnerabilities of the assets, and how to get all of that into our system planning models in order to make better decisions about adaptations and when they make sense. If you search for Climate Ready, you will find a whole host of resources available online, all freely available to the public. And we also will be wrapping up this initiative in the next 6 months with much, much more to come. And so hopefully we'll have even more answers soon. But to talk a little bit about how we've been thinking about resilience planning in Climate Ready, we're taking an integrated modeling approach. And the main reason for doing this is that the climate space is huge, and there is no one planning or simulation model that can adequately capture the whole space of climate risk that you might be concerned with. You need to understand natural variability, so considering a large number of weather years. You need to understand the uncertainties present of climate change. You need to perhaps focus on extreme events in some situations to really understand dynamic behavior of, for example, your transmission system, whereas in other cases you want a broader view of overall system risks. So there's a lot on this slide, and I don't expect you to take it all in, but you can sort of think about it as being broken down into these three main components. So there's a lot of work that goes into properly representing climate risk in our system models, right? So in something like capacity expansion or resource adequacy or production cost models, we want to make sure that we are consistently representing what climate change means in those models, both today, if you're looking at today's system, and in the future, if you're trying to evaluate changing risks and what that means for planning decisions. And then there's sort of the planning piece of, okay, we know we have climate change, we know we want to better manage climate risks, let's plan a system considering those explicitly. Once we have some proposed system plans, you can evaluate them using a whole host of models that are typically used today, including resource adequacy if we're concerned about this adequacy question. Because it's an integrated model, the consistency of assumptions is really important, and there's also the possibility of feedback loops because, again, no one model can answer every question that you might have, and so you might end up iterating back and forth to get to a robust solution based on the outcomes of a series of models. So I can walk through a little bit about how we do this and how we think about this, and I'll start with this representing climate impacts piece, which is really important and is a driver for how all of the rest of the models behave and interact with each other. So perhaps it's useful to first start with bounding the climate question. What does it mean when we say the climate is changing? What does that mean for the data that we use in our planning models? Here's an example of a specific location looking at the change in temperature distributions from today's climate to a 2050 climate, looking at both a low and high emission scenario. So there's certainly a change, right? You can see that shift in the distribution from the gray to either the green or the orange. Perhaps it's not drastic, but what does change quite a bit are the tails, and that's what we're most concerned with when we're talking about adequacy or resilience. And those tails, both on the high end and the low end, have different types of stressors for our grid and require different types of adaptations if we want to be able to make it through these types of events without load shed. And so this can help to sort of bound the problem of, okay, what does it mean to consider future climate data? What does it mean to put 2050 data into our model as opposed to historical data? We can also look at specific extreme events, and here I'm showing an example of hydropower risk, and this is in the United States because this is where we had the data available for, but this is a way of thinking about what sort of the bounds of scenarios might look like in a changing climate. And what this is showing is, there's a lot on this map, so I apologize, but what it's showing is for each hydro basin in the United States, what portion of the dams are expected to see increases or decreases in generation availability. And so if you're planning for sort of like the range of what is feasible, in some cases you can safely assume that you will see an increase in rainfall, in hydro availability, but in other cases that's not true, right? And so you have to take into account this range where even within the same basin, you might have some dams expected to see a reduction in water and hydro availability, whereas others, perhaps quite nearby, are expected to see this increase because of the complex nature of, the reservoirs and the hydro flows. And so if we're planning for extremes, you might want to make sure you capture the bounds, again, of these types of extremes within all of the dams that are relied upon by a single power system. Okay, and then we also know that climate change, climate conditions impact other aspects of customer response. So these are some plots looking at how future conditions may impact electricity demand. This is for a specific case study in the United States. So again, these assumptions are going to vary drastically based on where you are. But in this case, we see that electrification, changing technologies, and load growth are much bigger drivers than climate change, right? We see a climate signal moving from the blue to the yellow distribution here. The blue distribution is assuming that there is no climate change. We're just planning the system with our assumptions about load growth and technology changes. And adding that climate signal, again, adjust the tails, but only slightly. And so you really have to understand where the sensitivities are in your system, because getting the technology adoption piece wrong is going to impact your results much more than getting the climate piece wrong in this case. So if I have time, which I think I will, I can dive into some sensitivities around this as well. And then I talked about asset vulnerabilities, right? So every asset is exposed to the weather conditions, surrounding it at any given point in time, and that has direct implications for how it performs, right? You have capacity derates when things get really hot. We've seen, at least in the United States, a lot of failures, so increased forced outage rates when things get really, really cold if they're not properly winterized. We have increased failure rates during high wind conditions, for example. We have fragility curves. We have models that show changing maintenance schedules, reduced lifespans. All of these things are changes to the asset's performance that can, if you can quantify them, can be taken into account in a planning model so that your simulation of the operations is representing the reality of how those assets will perform. And so we can sort of aggregate these across all assets in the system, look at what the system can actually provide in terms of generation, transmission, and loads at any given point of time, and say that, okay, this is the climate-informed representation of grid performance. And then even when you have all of that, right, when you have the climate data piece, when you understand your asset vulnerabilities, you still need to choose your data to use in your models. And I hinted at this earlier, but we have these models that are designed to handle really different classes of data. So some typical production cost models or even resource adequacy models might be looking at a typical meteorological year. So representing a nominal year to make sure that we are meeting our economic targets. How do you choose a typical meteorological year if you're planning for climate risk? You obviously leave out the tails. Perhaps you want an extreme meteorological year, or perhaps it's important to incorporate a range of years so that you get both the natural variability and some good and bad years captured in there. You still want to capture that economic performance of the system, as well as its ability to handle these high stress events from an adequacy and resilience perspective. Separate from that, we also have models that might only be concerned with a single extreme event, right? Like, can I ride through this heat wave? Can I ride through this drought period? Can I ride through this hurricane? And those require, perhaps a 3-day, 3-week, 3-month outlook. They're not concerned with entire years or multiple iterations of years. And then we have other models like, transmission adequacy models that are looking at single hourly snapshots, right? You cannot capture climate risk with a single hourly snapshot. There is way too much there. And so if we're trying to choose the data that allows us to represent, the range of climate conditions, we have been using something that we've been calling risk screening, which is a very approximate way to down select data for use in these more detailed models. And so this allows you to take a massive amount of climate data. In the example here, we ran it through 720 synthetic realizations of a future year to assess the most stressful grid conditions. And so we aggregate all of those asset vulnerabilities, we couple it with load projections, and we say, hey, these are the sets of conditions that we think are stressful and perhaps need closer attention for planning. And so if you sort of think about this plot on the right of a depiction of weather, right, a depiction of many weather years, what risk screening does is, as I said, takes all of those conditions from asset performance into account and highlights periods of stress. What's important to note is that it might not be the most extreme periods, right? It might not be the single hottest day that is causing your system the most stress. It might be a 5-day warm period where you also have low wind production, and without wind, your transmission lines aren't cooling themselves, and you don't have enough wind generation to sort of augment to meet the demands on your system. And so it allows you to pick up on the non-intuitive stressors for the grid, separate from what is extreme from a climatological or meteorological standpoint. And we've used this in a few different ways. One of them is to down-select the data that we need to do computationally feasible modeling for different types of models. And so I can sort of walk through the examples here, but we've done capacity expansion modeling explicitly considering resilience, and so we sort of have your standard data that goes in for economic capacity expansion modeling, and on top of that, we augment it with extreme events to use separate constraints to make sure that we are able to meet load during those extremes. And so the top left panel shows how that might look if you use risk screening to say, okay, give me a handful of high heat events, give me a handful of low temperature events. Let's make sure that we can still build a system to handle these conditions. On the other hand, resource adequacy might want a large number of weather years, right? These models can handle a lot more data. They are computationally more tractable. And so we can make sure that we hand resource adequacy both nominal and severe weather years to say, okay, we want to make sure that we are capturing the natural likelihood of these high stress events. So let's get some good years, let's get some bad years, let's get a good mix for our resource adequacy assessments. For transmission reliability, again, you might want single snapshots. The most stressful snapshots in the transmission space are generally these high heat events, and so you might focus only on those extreme heat type events where your load is high, your assets are stressed, perhaps your flow has changed and is trying to direct flow to different parts of the system, and it allows you to select what you care about most. Okay, so that sort of walks through how we think about representing climate risk in the power system itself, and then we can move into this planning space, right? How do we actually plan a grid to be resilient, to be reliable, to be adequate? And so as I mentioned, we have resilient capacity expansion research that we've been exploring, where we do baseline planning, where we account for the economic cost optimal plan to meet future demand, subject to whatever decarbonization objectives you might have. And then we also compare that to resilient capacity expansion planning, where we hand the model a series of extreme event snapshots, and we allow it to both build a different system and to include hardening at the optimization step. So it can include adaptations to both existing assets and to new assets that it's building. And the way that we've been sort of constraining this is using a target we've called loss load tolerance. So in this planning space, how much loss load are we willing to tolerate for these extreme event conditions? And you end up with a curve, right? A trade-off curve of, okay, if I want to allow for 0% loss load, it's going to be a more expensive system. And again, this is a planning target. This does not mean that the actual system will meet all load under all situations, because you can only hand it a few extreme events to plan for. But you can then take these different proposed system build-outs and evaluate them using a much richer data set of climate conditions and get a sense of whether you are actually building a more resilient system if you move towards this lower loss load target. Okay, so also I want to point out that you do build different systems, right? Your loss load tolerance dictates what you build, it dictates how much you build, It dictates how much hardening you put on. In this case, we handed the model a series of hardening options for assets to deal with both high temperatures and low temperatures. And so we allowed natural gas plants to install inlet air chillers so that they could better operate at a higher capacity during high temperature events. We allowed thermal units to winterize so that they could ride through extreme cold events as well. And there were some other adaptations shown as well. But basically, these are optimized within the model itself. And each portfolio gives you a proposed system build-out that you can then evaluate. In this case, I'll talk through some resource adequacy results. Okay, so we built a system. We have all of these proposed options. And then moving through to resource adequacy, in this case, we wanted this to be climate informed, right, to represent whether this system will be adequate in a future year. We're looking at 2050 here, so building a grid to meet 2050 demands with resilience targets, and then evaluating it based on projected conditions for the year 2050. Again, resource adequacy is able to capture interannual variability, so we handed it 71 synthetic future weather years that represent the type of natural variability that we've seen in the historical record. You end up with a lot of data as you go through the sampling approach. You get a lot of information about how the system is likely to respond, and we make sure that all those ways that we incorporated climate risk that I talked about earlier are captured here. So we have climate-informed loads, right? So the loads are temperature dependent. We have D-rates on thermal units based on temperature. We have higher forced outage rates based on weather conditions. If it's extremely cold or stormy or whatnot, we can model these higher forced outage rates. And this is where we sort of get this climate piece captured. And so if you look at some results, right, we have sort of standard resource adequacy metrics. We can look at the loss of load expectation. We can look at the expected unserved energy, loss of load hours. Again, the baseline system is if you don't account for these extreme events. You're not planning for resilience explicitly in your system modeling. The LLT are those two loss load tolerance targets that I mentioned earlier. So you're handing the model extreme events and you're saying you need to either meet all of the load, right? So 0% loss load is allowed, or you are allowed to lose up to 10% only during these extreme events. And you see a drastic change in these metrics for these different systems, right? So if you plan for a system to be able to ride through extreme heat and extreme colds, it does a lot better in terms of actually meeting the demand, right? This is intuitive, and it's great to see the results play out this way. But the results are drastic, right? The increase from 7 megawatts expected unserved energy to almost 19 gigawatts is a drastic change from these systems. And so if you do not incorporate climate change, if you do not incorporate resilience explicitly, you're leaving a lot on the table that you will likely have to deal with down the line when perhaps it's more expensive. Just to give you a little bit of a sense of what this looks like in practice, so you can see sort of the distribution. I should have mentioned this is an example in Texas in the United States, and so we have a lot of summer risk, especially looking out to 2050. And so you can see that risk picture is quite reduced. The winter risk is almost entirely reduced, and the summer risk is still there a little bit in the LLT 0 case, but barely so. Again, looking at what the system actually does, it basically builds more resources and makes sure that those resources are more available to meet loads. So this is a single snapshot of an event that the baseline system was not able to meet, right? So we had loss load in the baseline case. We had a small amount of loss load in sort of that moderate resilient system. And in the most resilient system, we were able to capture it by building the right amount of resources to handle this type of condition. So I talked about sort of that I showed that picture of the load projections and how technology adoption is so much more of a driver than temperature or climate change considerations. And so we actually dove into that a little bit, recognizing that, okay, we're doing a really good job understanding the climate piece, but what about that load piece, and are our assumptions good enough? And so we actually did a sensitivity case here where we modified our load projections to include higher electrification rates in this case study and to apply more conservative assumptions about the efficiency of these end-use technologies. The original data assumed that most of these technologies would become more efficient over time, and you'd have a net actual decrease in load in some cases because of those efficiencies. And so we did a sensitivity analysis to say, okay, if we change those assumptions, we get this much higher demand projection, right? So our 2050 demand looks a lot higher than it did previously. We built more capacity in the model to meet those demands, and then we can evaluate that from a resource adequacy standpoint. And so you can see for what is supposed to be the most resilient case, right, this loss load tolerance of 0%, saying we tried to model a system that met all of the demand during these extreme events, we have much higher loss of load expectation, much higher expected unserved energy metrics. And we see that the system, that top plot is showing that the system is really struggling during some afternoon, evening hours to meet demand. Okay, so this is sort of a perfect example of why we have the potential for feedbacks in our integrated modeling platform is because we are clearly not good enough, right? We need to go back to the drawing board. And so in this case, we can use this outcome to feed some specific events at these high stress afternoon hours back to capacity expansion to say, okay, here's some more information, here's what you're missing, let's see if you can better handle these events. So doing a round of iteration, we improved these metrics quite a bit, right? The loss of load expectation was reduced by a factor of 4. That's great. But it's also telling us that, we're still missing a lot. This is not yet at a level, this metric is not yet at an acceptable level, and we need to go back to the drawing board. I'll be the first to admit that this is still an open area of research. There's a lot more that we need to do here to figure out how to sort of close these gaps, right? Do we hand more extreme events to the capacity expansion? Do we change the way that the capacity expansion is handling resilience? Do we change those metrics around what we are targeting from a resilience standpoint? Do we do something else, right? Like we are actively thinking about how to make sure that this is a computationally tractable problem, that it doesn't take 5 or 10 or 15 rounds of iteration to get you to a solution, that you can do it the first or the second, maybe the third time, right, to make sure that we understand the type of data that results in robust solutions for a capacity expansion model. So just a plug that I'd say iteration works, right? The integration of these models works, but there's still a lot that we don't know about the best data to put in and the best practices to get the right results out. So that's really all I have. I will end with just a few takeaways about how we're thinking about climate resilience, and I'd say climate resilience goes hand in hand with adequacy, as I started with. We do need to change our traditional planning practices. Climate change is warranting a consideration of forward-looking conditions, even if they are uncertain, and they are uncertain, but we can no longer look to the past. We need those models to incorporate realistic representations of how assets will perform in a changing climate, and that is not something that is perfectly understood, and there's, again, a lot of uncertainty there, but something is better than nothing. And you need more than one model to really consider the space of climate change. If you're using multiple models, you need to have consistent assumptions about climate data, about your assets, about all of your scoping, about future changes to the system, future policies. They need to be consistent so that these models can actually work together and provide you robust answers. In terms of resilience and adequacy, they can go hand in hand. Addressing resilience is more than just adequacy, but you can go a lot of the way by improving the adequacy of your system. And then I think that this is where sort of some secondary metrics come in to capture the meaning of the outages, right? Who is losing power? What are the consequences to customers, to society of those outages? And I think this is really where resilience picks up and adequacy ends. Doing it well, right? Like doing this iteration between resilience and adequacy and understanding all of the implications from your different models is really hard, and there's certainly some art in it as well as science. But we will have hopefully some pretty robust guidance coming out from EPRI soon on at least some scientifically grounded approaches to doing this well. That's all I have. Thank you.